Hey everyone, my name is Matt Kosovec, CEO and co-founder of DataForge, and today we're going to be talking about the fundamentals of the DataForge framework, some of the core concepts behind it, some of the core theory that goes into it, as well as the history of other frameworks and other approaches to building data platforms, data engineering solutions, some of the challenges that are involved with them, some of the anti-patterns that have been implemented in the past, and what we're doing at DataForge to bring data engineering to the future, automate the tedious, and simplify the complex. With that, let's jump right into it with a review of some of the historical patterns in data engineering. So here we have a traditional, we'll just call it stored procedure based with no framework, no governance around the different patterns involved within the transformation pipelines. You can think of each one of these black boxes as, again, a stored procedure, a SQL script, or some other type of transformation, whether that's in an ETL tool that generates it or otherwise. Some of the anti-patterns I want to highlight here are where you have multiple different packages or procedures writing to the same table. The main downside of this is if you have some type of issue in a downstream area or some type of bug or challenge, it's really difficult to understand what exact piece of code within either one of these, or in this case there's just two, but maybe there's 30 of these all affecting this single table. And if there's an issue with the data here, it becomes nearly impossible to diagnose exactly what and how happened to that data element and where exactly to fix the problem in the upstream logic. Similarly, when you have these looping back type of bits of logic where you have something writing to it and then writing back from the same data set, that makes things even more complicated because oftentimes it's a solution where you don't even know, hey, was it on the first run or the second run or the third time that this thing kind of ran through its cycle that the issue occurred. And that makes, again, really challenging to understand what exactly broke, how it is involved. And as a new developer coming into this solution who's never been into this logic or didn't build it themselves, it's really challenging to follow exactly how everything is connected and why exactly it was developed that way. Ultimately, when we talk about the scope of concern, we talk about what an engineer needs to worry about, what they need to think about whenever they're either building this from scratch or they're coming in as a break fix person, or hey, we need to add a new bit of logic or a new element from one of these new tables or a new calculation to a target table. And with these patterns where you have multiple things affecting the same table, you have these kind of write back operations. It ultimately means that the developer needs to think of almost everything all at once, right? Because anything can touch anything at any time, any one of these packages could touch any table, they need to figure out exactly what it's touching and then what does that table touch and how does that one work, and basically trace the entire bit of logic. Maybe they're getting some help from an observability tool or some other lineage capability to help them with that. But ultimately, they need to think about everything, oftentimes all at once, as part of their change or their edit of the logic when they need to add data or fix something in the solution, which becomes extremely time-consuming and challenging to do impact analysis and otherwise. This is a major challenge, and next up, we're going to talk through some of the more modern frameworks that have helped to reduce this challenge and simplify this dynamic. Moving on to the more modern frameworks, you can see our picture here has gotten a lot simpler. We now no longer have the ability to write to multiple different tables or have multiple different bits of logic writing to the same table. And this concept is called immutability. And so this means that every single table that you're producing in your transformation logic has one and only one bit of code that is affecting it. There's a very powerful concept introduced originally by Spark, and then DBT and other solutions similar to DBT or derivatives of DBT take the same approach, and they call them models or nodes or whatnot to help, again, compartmentalize logic in a way that ensures that you don't have those issues that we talked about as part of the kind of free-for-all strategy. With this new approach, you now have developers no longer needing to consider everything everywhere all at once. They only need to think about, all right, what are the tables that are the inputs to my bit of logic here, and what exactly am I trying to produce as my output in this table? Everything they're doing, though, is at the table level. They have to think about everything that's happening in all the tables that are happening upstream, and they have to think about everything that's happening in the target table, both across rows, dimensions, filters, aggregates, everything happening. But it's a huge step forward. Again, Spark introduced this with data frames in the immutable data frame. And then, of course, again, DBT with their models and SQL wrapper, or so the wrapper around SQL logic to help developers, again, simplify these major problems and introduce these more functional patterns and declarative patterns to their transformation code. And this also helps with things such as orchestration. So without having multiple things touching this target table, the coordination and logic of what needs to run first, second, third becomes much more straightforward because there's only basically one way to do this. You no longer have a decision point of, hey, if we have two things writing to this table, which one runs first, right? In databases, you can't have two things writing to the same table at the same time. So oftentimes you'd have to, again, decide which one needs to run first, second, third, or they need to run the first one first, and the second one, then back to the first one. All of those patterns are now eliminated from the possible decisions that developers need to make. And that's a core concept that we're going to then explore more with the DataForge concepts is the less decisions developers need to make and the more that they can focus on the core business logic, the actual relational algebra, if you will, that needs to be implemented, and the less they need to focus on all of these decision points in one path or the other that they could take, the better in terms of the efficiency and their ability to get more work done and focus on just what's important, which is using their minds to write complex logic and create the target tables, create the target elements that they need to. So next up, we're going to talk about the DataForge framework. And again, just to round this out, we started from everything all at once, we're at the package or solution level. We've now broken it down to the table level. So now rather than having to worry about everything, we just have to worry about the input tables and output table. And then with DataForge, we're going to talk about breaking it down further and helping to simplify this into the next layer, and then some core concepts behind how we did that. All right, moment has come. Time to actually start digging into DataForge and how we approach things a bit differently. So as you can see here, our diagram has evolved yet again. And the big change here is that rather than thinking about things at the table level, what's lower than a table? Well, it's rows and columns. And specifically with columns, we're going to start digging into some concepts about what we call column pure and row pure in the future. But this is the core concept that is foundational to DataForge, is rather than worrying about tables in, tables out, we're allowing developers to think about just columns in, column out for each and every rule, rather than having to think about the entire table, everything happening in that table, all the logic that built that table. You can think about just what happened to the specific column that you're using within the rule you're writing or the smallest SQL expression you're writing, and being able to reduce the scope of concern, as we call it, to the column level is dramatically helpful whenever you get into these really complex, really large deployments with thousands or tens of thousands of lines of code. If your developer then is able to go into a solution and understand exactly what line of code affected a data element in a table, and then exactly what that change will do downstream, upstream, and otherwise by just changing a single bit of code, they're then able to, again, take what the Spark and DBT did with their table and take it, again, to the next level, to the next generation of data engineering tools, which then, by using this core concepts of column level transformation, it has tremendous benefits. Again, similarly, how the orchestration side became a lot simpler whenever you had to think things at the table level. The same kind of multiplier happens whenever you break it down to the column level and are able to automate things even further. The core concept, though, with DataForge and with breaking things down to the column level is that not everything fits into column transformations. Oftentimes you need to change the number of rows, whether that's a group by or a filter or some other type of aggregate or explode function or cross join or otherwise. And so what in order to take advantage of this column level transformation, we needed to look at all the different type of SQL code that you write and figure out how to break it down into two different groups, what we call column pure and row pure. We're going to dig into those concepts next, but those concepts are now fundamental about how you can take advantage of this next layer of evolution by thinking about things purely in a columnar fashion. But in order to do that, you have to, again, learn a little bit and understand a bit more about how you can write your code a bit differently, how you can fit it within the DataForge framework by writing it a bit differently. And by doing that, then you get all the advantages, again, similarly, not just for building your code, but evolving it, expanding it, extending it, and organizationally, right? If you have multiple developers or a large team of developers all building in the same architecture, how does everyone follow similar patterns, and how does everyone build code effectively without stepping on each other's toes or causing issues? So with there, we're going to start digging into what I meant by column pure and row pure. We're going to talk through some examples of what that relational algebra looks like. We're going to keep things relatively technology agnostic and just focus on the core concepts. Then we're going to round it out by some of those advantages I mentioned. Again, some of it was pretty self-evident when we went from package level or solution level to table level. It's a little bit less intuitive when you think about going from table level to column level, and we'll talk about those as a final wrap up for this section. All right, let's talk about column pure functions. So the concept is relatively simple. The idea is, rather than thinking about an entire table and all the different types of transformations that are possible in a SQL statement, we're going to think about just the types of transformations and just the types of SQL statements that do effectively adding a new column to an existing table and without changing the number of rows. So you can think of this as, you have your Excel sheet and you are then adding a new formula and dragging the formula down the list of existing rows in order to calculate that new column. So in this example, we have columns A and B, and we maybe add them together. A plus B, or A times B, is equal to X. And we then take the result of that, and because it has the exact same number of rows, we can add it to a column to the existing table. And so rather than thinking about table in, table out, we can think about adding a column to the existing table that is already set up and stored without affecting any of the original data sets. So again, this is a really simple concept. We're going to jump into some of the examples here. So all of your kind of scalar operations, as I mentioned, right? Revenue times 100, or revenue times quantity, or something like that. Aliasing, right? Renaming a column is also column pure. Probably the most simple version of it, right? You're not doing anything. You're just adding a new column with a different name that has the exact same data as an upstream column. Multiple column operation. You can do 2 or 3 things all put together. Where things get interesting is some of the lesser used, lesser known syntaxes of SQL, such as window functions. So here you can do an aggregate, and you can look over multiple rows within the table, and you can calculate the sum, you can calculate a rank, you can calculate an average, and save that value as if you were typically doing a group by or some other type of more traditional aggregate syntax. But by using this syntax, you're not changing the number of rows. You're just adding a new column that for every row it has the appropriate result. And that, again, has a lot of benefits because you're remaining column pure by doing that calculation with this syntax in this fashion. As we mentioned, ranking's another one. Again, just kind of a different type of window function. So these are pretty simple. Again, and in our previous example, we had 2 columns creating just 1 column. Where things get interesting, though, is by chaining these together, right? So in this example, we have the 2 columns, A and B, creating X1. And then our second jump here, we're going to use the result of X1 and maybe column B again. This could be column C, could be a different column, in order to then calculate X2. And so what you can see now is you can slowly but surely chain logic, right? So X1 is dependent on A and B. X2 is dependent on X1, which is dependent on A and B. And so ultimately you can say, all right, these 2 things, right, we can then chain this logic together. And so you can think about doing this over and over and over again, right? 50, 100 times, in order to continue to write your calculations and chain your logic together by adding new columns, rather than having multiple stages or layers or saved tables or models or nodes or packages. You can do as much of it as you can all within one table by continuing to chain these columns and chain these functions, as we call them, together in order to get your ultimate calculations done. Now, extending this concept of a simple calculation, all using columns from one table, to something more complex, which includes joins. Oftentimes, the only time you're building a data platform is to combine data from multiple tables or multiple systems or solutions. And so without including the joins in this framework, it would be very limiting. So let's walk through an example here. We have our base table here, as we call it, T1, and then a separate table here, a lookup table, L1, and we have a join condition between the two. Some important things to consider when thinking about column purity is the cardinality of the two tables that you're joining together. So again, what we want to do is to connect the two tables and retrieve data from one of the lookup tables, in this case the M column, and take that result and add it as a new column to the existing table T1 as our result R. But we have to do this without blowing out the grain, as we call it, or creating new rows, or potentially causing any filtering as part of this join condition. So if in the example we have a many to one cardinality between our base table T1 and L1, then we're guaranteed not to cause any join condition that would create extra rows within the T1 table. So you can think of it as a left join, a lookup, essentially, where we're going to join between C and C2, make those equal to each other, and then we're going to take the result of our select statement of M and add it as a new column. So our result of the data, oftentimes you'll get duplicates in M sub R here, where maybe if you have X and Y in row 1 and row 2 here, within MR you'd have maybe X, X, and Y, right, as your result here. But it's all okay. This is a valid column pure function because we now have added a new new column to the existing table utilizing a upstream function. And we did that without changing the number of rows. Therefore, we fit within the framework and we can do these types of calculations and solutions without any issue. Some SQL examples of what this looks like is a basic left join. This follows kind of the same pattern we just talked about, right? We're going to join on an ID and we're going to grab a column from a lookup table, right? So we're going to grab this customer C. We're going to grab the C name table from customer and we're going to alias it as customer name. This is all legal within the column pure framework. So again, transformations or joins that look like this are good so long as the cardinality from invoice to customer is many to one. However, we can operate over many to many relationships or one to many cardinality joins, again, moving from the base table to another table by including an aggregate function as part of essentially the subselect for that table. And what we're doing here is converting that many to many or many to one cardinality to a one to one in the join condition by doing some type of roll up or some type of calculation prior to joining the two tables together to avoid creating new rows through that join condition, right? Because if you have a one to a many, you're going to be creating new rows, aka duplicating data from the one side to the many side. So going to a visual example of that second solution, we now have, again, our same base table here, ABC. However, we now have L1, and L1, as you can see, has 4 rows, and T1 has 3. And this is a different table. It's an aggregate, a many cardinality. If you were to join these directly from C to C2, you would result in 4 records or maybe even more records as part of joining these two because the cardinality is, again, one to many. So in order to avoid that grain change or, again, blowout of grain, we need to run a function, a pre-function on L1 in order to aggregate the data up to or roll up the data to the grain of T1. So what we're going to do is maybe run a sum of the M column and sum or some other type of aggregate. And then we're going to run a distinct on that result over the join condition or over the join column of the T1 that we're going to then join together. So again, by essentially converting the original table up to a new logical table that has a one-to-one cardinality with the original table, we're able to get the result of that calculation and use it as a column pure function and maintain all the benefits of working at the column level and only having to think of things at the column level and working through the DataForge framework and chain these functions together. So this is just, again, another example of showing how there's a wide swath between window functions, between join conditions, between rollups of relational algebra. It's a large portion of all the logic that you need to do on a data set is actually able to be fit within this concept of column purity, right? Which is creating a new column without changing the number of rows, which then gives you a tremendous number of benefits. So again, the core foundational thing with the DataForge framework is look at all of my logic and try to figure out how much of my logic can I rework or rethink to fit within this concept of column purity, either by refactoring it or reorganizing it or writing it differently as maybe a window function or a combination of aggregates and distincts here to fit it within this framework and this concept in order to allow my developers and allow my team and myself to work at the column level rather than having to think at the table level, which again brings you to this next generation of efficiency and automation for all the other considerations within the architecture. All right, so as promised, we're going to now talk through an example of what some of the benefits of this column level configuration, this column level way of thinking helps people to build out these solutions and work through them. We're going to quickly talk about row pure functions and row pure transformations. What you can think of row pure as is essentially taking the guardrails off and saying, look, we can change the number of rows, but ideally we're not going to change the columns or add or remove any columns as part of the calculation or the table statement. So again, something such as a group by statement, right? Very typical select, group by, etc. Many times those are a combination of column and row statements, right? You're maybe creating some new sums, you're creating some new aggregates, while you're maybe running a distinct on some other columns, right, as part of your group by, which means you're kind of combining and blending those two things together. Ideally, you would, example, write a window function to perform the aggregate, and then separately in a separate stage in your processing chain or in your orchestration, you would then run the distinct function secondarily. And by breaking the logic down that way and putting all the column pure logic together into one stage, right? So adding the column pure logic or centralizing the column pure logic into one layer, you get a lot of benefits and again, a lot of advantages that come with that. One of the advantages of column purity and separating out column pure from row pure is by just the kind of simple addition of adding a new column to a table. If you don't have this intermixing of the two logical constructs of column and row pure, the regression testing becomes really straightforward. So let's look at an example, right? We have our base table, we have our 3 columns, right? We now write a new column pure function. We added this function to the existing set of logic that was already within this stage. And by that, we've added a new column. We've added a new attribute to this data set or a new calculated field. And then we then run it through the same, again, row pure stage, which again, maybe is a distinct or a filter or some other type of solution that does not change the number of columns or affect the columns in any way. It just changes the number of rows with some type of filter. And because this row pure stage has no reference to the new column or the new attribute we've added, it can be safely persisted through with the same filter. Again, the existing filter on this did not have any references to this new column by definition because it was the existing, it was only referencing the existing columns, which means that you can easily just persist this new column as a target column without having to regression test everything else, right? So again, you only get into trouble with regression testing at the logical level whenever you intermix these things together into a single SQL statement. And so looking at the kind of secondary side of this, where we talked about adding a column pure bit of logic to this chain, let's talk about adding a row pure bit of logic. So whenever, again, you need to add this new row pure bit of logic, aka a new filter, a new distinct, a new explode function or cross join or something like that, we're going to, again, try to take as much of the column pure logic as possible, put it into this stage, but we now have a new filter, right? A new target data set that has maybe, again, a different filter on it, or a different aggregate level, or, it needs to be by date. In order to do that, we're going to then just branch off the logic, right? We'll take the result from the column pure stage, and we can then create a parallel branch of row pure logic to create that new data set. AKA, we kind of go to the table level whenever we think about the row pure stage. But the nice thing is, because we're not bleeding and blending row pure and column pure stuff together, this becomes a very straightforward and simple package, or a simple set of logic to understand for someone to come in, again, after the fact and trace the lineage and figure out exactly how and what way things are happening throughout the solution. So hopefully this video gives you a good overview of exactly what we do to break down the logic within DataForge. We have a lot more material around this, but fundamentally, the major concept to think about when working in DataForge is with the really old stuff, you had to think about everything all at once. DBT and Spark introduced the concept of immutable tables. We at DataForge, now with this introduction of breaking down your logic into column and row pure functions and requiring developers or thinking about your logic in a way to get as much stuff into this column pure fashion as possible. If you do that, you can then take things at the column level, and you can think about immutable columns rather than immutable tables, which dramatically reduces your scope of potential impact, has tremendous benefits for the long-term expansion and growth of the platform over time, and ensures that all developers are taking the same approach to their stage development, their orchestration, their patterns that they are trying to work together on collaboratively. All of that comes together in a really powerful and efficient way. Again, if you are able to take this next step and move into the future by working with columnar level logic and thinking just, hey, I got these input columns and my output columns, and everything else is taken care of for me because I, again, are following this framework. So that's it. We're going to have some more material coming out soon. Thank you very much for your time, and please, looking for feedback, questions, or comments, please leave them down below, or send us an email at info@dataforgelabs.com. Thank you so much.